Preface. In traditional natural language processing, NLP, systems, language entries such as words and phrases are taken as distinct symbols. Various classic ideas and methods, such as n-gram and bag-of-words models, were proposed and have been widely used until now in many industrial applications. All these methods take words as the minimum units for semantic representation, which are either used to further estimate the conditional probabilities of next words given previous words, e.g., n-gram, or used to represent semantic meanings of text, e.g., bag-of-words models. Even when people find it is necessary to model word meanings, they either manually build some linguistic knowledge bases such as WordNet or use context words to represent the meaning of a target word, i.e., distributional representation. All these semantic representation methods are still based on symbols. With the development of NLP techniques for years, it is realized that many issues in NLP are caused by the symbol-based semantic representation. First, the symbol-based representation always suffers from the data sparsity problem. Take statistical NLP methods such as n-gram with large-scale corpora, for example, due to the intrinsic power law distribution of words, the performance will decay dramatically for those few shot words. Even many smoothing methods have been developed to calibrate the estimated probabilities about them. Moreover, there are multiple grained entries in natural languages from words, phrases, sentences to documents. It is difficult to find a unified symbol set to represent the semantic meanings for all of them simultaneously. Meanwhile, in many NLP tasks, it is required to measure semantic relatedness between these language entries at different levels. For example, we have to measure semantic relatedness between words, phrases and documents in information retrieval. Due to the absence of a unified scheme for semantic representation, there used to be distinct approaches proposed and explored for different tasks in NLP, and it sometimes makes NLP does not look like a compatible community. As an alternative approach to symbol-based representation, distributed representation was originally proposed by Geoffrey E. Hinton in a technique report in 1984. The report was then included in the well-known 2-volume book Parallel Distributed Processing, PDP, that introduced neural networks to model human cognition and intelligence. According to this report, distributed representation is inspired by the neural computation scheme of humans and other animals, and the essential idea is as follows. Each entity is represented by a pattern of activity distributed over many computing elements, and each computing element is involved in representing many different entities. It means that each entity is represented by multiple neurons, and each neuron involves in the representation of many concepts. This also indicates the meaning of distributed in distributed representation. As opposed to distributed representation, people used to assume one neuron only represents a specific concept or object, e.g., there exists a single neuron that will only be activated when recognizing a person or object, such as his, her grandmother, well known as the grandmother cell hypothesis or local representation. We can see the straightforward connection between the grandmother cell hypothesis and symbol-based representation. It was about 20 years after distributed representation was proposed. Neural probabilistic language model was proposed to model natural languages by Yoshua Bengio in 2003, in which words are represented as low-dimensional and real-valued vectors based on the idea of distributed representation. However, it was until 2013 that a simpler and more efficient framework Word2Vec was proposed to learn word distributed representations from large-scale corpora. We come to the popularity of distributed representation and neural network techniques in NLP. The performance of almost all NLP tasks has been significantly improved with the support of the distributed representation scheme and the deep learning methods. This book aims to review and present the recent advances of distributed representation learning for NLP, including why representation learning can improve NLP, how representation learning takes part in various important topics of NLP, and what challenges are still not well addressed by distributed representation. Book organization. This book is organized into 11 chapters with 3 parts. The first part of the book depicts key components in NLP and how representation learning works for them. In this part, Chapter 1 first introduces the basics of representation learning and why it is important for NLP. Then we give a comprehensive review of representation learning techniques on multiple grained entries in NLP, including word representation. Chapter 2. Phrase representation is known as compositional semantics. Chapter 3. Sentence representation. Chapter 4. And document representation. Chapter 5. The second part presents representation learning for those components closely related to NLP. These components include SEMME knowledge that describes the common sense knowledge of words as human concepts, world knowledge, also known as knowledge graphs, that organizes relational facts between entities in the real world, various network data such as social networks, document networks, and cross-modal data that connects natural languages to other modalities such as visual data. A deep understanding of natural languages requires these complex components as a rich context. Therefore, we provide an extensive introduction to these components, i.e., SEMME knowledge representation, Chapter 6, World knowledge representation, Chapter 7, Network representation, Chapter 8, and Cross-modal representation, Chapter 9. In the third part, we will further provide some widely used open resource tools on representation learning techniques, Chapter 10, and finally outlook the remaining challenges and future research directions of representation learning for NLP, Chapter 11. Although the book is about representation learning for NLP, those theories and algorithms can be also applied in other related domains, such as machine learning, social network analysis, semantic web, information retrieval, data mining, and computational biology. Note that some parts of this book are based on our previous published or pre-printed papers, including 1. 11. In Chapter 2, 32. In Chapter 3, 10. 5. 29. In Chapter 4, 12. 7. In Chapter 5, 17. 14. 24. 30. 6. 16. 2. 15. In Chapter 6, 9. 8. 13. 21. 22. 23. 3. 4. 31. In Chapter 7, and 25, 19, 18, 20, 26, 27, 33, 28, 34, in Chapter 8. Book cover. The book cover shows an oracle bone divided into 3 parts, corresponding to 3 revolutionized stages of cognition and representation in human history. The left part shows oracle scripts, the earliest known form of Chinese writing characters used on oracle bones in the late 1200 BC. It is used to represent the emergence of human languages, especially writing systems. We consider this as the first representation revolution for human beings about the world. The upper right part shows the digitalized representation of information and signals. After the invention of electronic computers in the 1940s, big data can be efficiently represented and processed in computer programs. This can be regarded as the second representation revolution for human beings about the world. The bottom right part shows the distributed representation in artificial neural networks originally proposed in the 1980s. As the representation basis of deep learning, it has extensively revolutionized many fields in artificial intelligence, including natural language processing, computer vision, and speech recognition ever since the 2010s. We consider this as the third representation revolution about the world. This book focuses on the theory, methods, and applications of distributed representation learning in natural language processing. Prerequisites. This book is designed for advanced undergraduate and graduate students, postdoctoral fellows, researchers, lecturers, and industrial engineers, as well as anyone interested in representation learning and NLP. We expect the readers to have some prior knowledge in probability, linear algebra, and machine learning. We recommend the readers who are specifically interested in NLP to read the first part, Chaps 1 to 5, which should be read sequentially. The second and third parts can be read in selected order according to readers' interests. Contact information. We welcome any feedback, corrections, and suggestions on the book, which may be sent to luzi@tsinghua.edu.cn. The readers can also find updates about the book from the personal homepage. http://nlp.csai.tsinghua.edu.cn//Luzi/ Ziyuan Liu, Yangkai Lin, Maosong Sun. Beijing, China, March 2020.